I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
That's one small step for man, one giant leap for mankind.
Hello, my name is Jose Hurtado, and I'm a professor in the Department of Geological Sciences at the University of Texas at El Paso. Today I'll be talking about science operations on the moon. To understand why we need to do science operations on the moon, we need to understand the scientific motivation for going to the moon in the first place. There's a number of questions that can be answered by exploring the moon. These involve issues regarding the origin of the Earth-Moon system, how the moon formed, and what are the basic processes that were important in the subsequent evolution of the moon. So how does a magma ocean work, for instance? What was the cause of the global asymmetry of the moon? And what's the thermal history of the moon after it formed? Other important issues are the history and the evolution, the vertical and lateral structure of the lunar crust, and the processes that produce and modify the lunar regolith and form the landscape on the moon. Going deeper, there are issues concerning the composition and structure of the lunar interior that we need to resolve, and these are going to require the installation of geophysical networks on the lunar surface. Going outward, it's important to understand the nature of the very thin lunar exosphere and the processes that govern the dust environment on the moon, and these are going to require the installation of environmental monitoring instrumentation on the lunar surface. A very important issue regarding lunar exploration as well as science is the nature of lunar water. That is, water that is deposited on the lunar surface by various processes and sequestered in cold traps, many near the lunar poles. At a larger scale, it's going to be important to understand the impact history recorded on the lunar surface and how it's varied over time. These are very critical questions that address issues for solar system chronology as well as lunar chronology. And so this is going to require focused sampling and the acquisition of context data in a geophysical and geological way. Another important question is how the formation and evolution of the moon and its well-preserved record of impacts relates to the early history of the Earth and the solar system as a whole. The lunar surface is a Rosetta Stone for this very early part of solar system and Earth history that is otherwise absent on the Earth. Another question is how and why the moon is different than other planets, including the surface processes, its thermal history, and its geological evolution. Other important questions are how the Apollo geophysical measurements, geological observations, and samples are or are not representative of the moon as a whole. And it's going to require global exploration of the lunar surface to address those questions. A final question is, how do we explore planets? What kind of measurements are needed? What strategies are effective? Do we use robots only? Do we use humans? Do we use a combination of the two? What sort of mixture of orbital and ground-based measurements, in situ analyses, or sample return are the most effective for getting the optimum science for exploring a planetary surface? The moon is going to offer us a great opportunity to test these strategies before we go onward to Mars and other planetary surfaces. What sort of exploration science tasks are going to be required to answer these sort of questions? Well, they involve many of the sort of tasks that field scientists here on Earth do. That includes field observations, the collection of samples, obtaining imagery, and also installation of instrumentation. And those could be geophysical instruments, environmental monitoring instruments, as well as in situ analysis of samples. Field geology is the basic task that astronauts exploring the lunar surface are going to be engaged in. The goal of field geology is to constrain the number of plausible geologic histories of a study area. And the approach to this is to iteratively test multiple working hypotheses based on field observations and simple data that's collected. These data sets could be qualitative descriptions as well as quantitative measurements using instruments. The products of this are going to be notes for Earth sketches and maps, for planetary surfaces, images and voice descriptions. And all this data is contextualized spatial data that can then be used in an integrative way to validate interpretations, test multiple working hypotheses, and most importantly, provide context and insight that can then inform follow-up data and exploration. An important thing to understand about geology is that it is a spatial science, so context is critical. It's also an historical science, and so it requires four-dimensional thinking. So there's a time component that's very critical to be obtained, and that can be done qualitatively in the field by looking at field relationships, as well as more quantitatively looking at the data from samples that are eventually dated and otherwise analyzed. Geology is also a process-oriented science. So one of the mantras that a field geologist keeps in mind is process from product. Looking at the products that we see in the landscape and the geologic record, can we infer the processes that form them? And then finally, a good geologist is skilled at pattern recognition. And so to do that, a geologist needs to maintain situational awareness. And that's one of the technological challenges, especially for doing field geology on another planet, of how you present to the field geologist the data that's necessary to maintain that situational awareness. A process for doing this is to remember the mantra, look odd, look ODD, observe, describe, and document. Basically, a geologist needs to look around. What is around them? What are the hypotheses being tested? A geologist needs to observe. So look at the terrain around you, the geologic record, keeping in mind things like process from product and the importance of the fourth dimension of time. Describe what you see in a very quantitative and also qualitative way, and then document what you see so that it can be communicated to others. To help a field geologist do their work on a planetary surface, there are a number of tools and instrumentation that are at their disposal. There's been significant advancements since the Apollo exploration of the moon. In particular, our exploration of Mars has shown that in situ analysis using miniaturized and mobile analytical tools is invaluable for understanding the geologic context of a field site. In addition, there's new geophysical and geological instrumentation that's used here on Earth that can be very easily applied to planetary exploration. All this field instrumentation needs to enable various important things to be effective for planetary exploration. One of the things is to enable the high grading and down selection of samples that are brought back to Earth. Reducing the return mass and volume is very important for engineering purposes. Another important task that instrumentation should do is the strategic generation and tactical modification of traverse plans, and also the real-time engagement of scientific insight into the geologic site that's being studied. Now, none of these tools are intended to replace crew expertise or to replace training for crews going to the moon. They're meant instead to enable and to increase the effectiveness and also the efficiency of the activities these crew members are going to engage in. A number of requirements need to be met for planetary tools and instrumentation. Probably first and foremost is that they need to be easy to use, especially by crews in spacesuits on EVA that are working in a pressurized suit with pressurized gloves. Tools are also going to need to enhance scientific situational awareness to provide data to the crew member in near real time in order for them to make decisions as far as how to change their traverse plans to increase scientific efficiency and also scientific yield. Tools should also promote better coordination of human and robotic efforts, as well as coordination between the crew members on the lunar surface and their science support team back on Earth. At the same time, these tools should maximize autonomy and facilitate decision-making without the need for consulting mission support on Earth. One class of tools that's going to be very important on the lunar surface is geophysical instrumentation. Astronauts and robots together may deploy and tend these geophysical instruments. Geophysical instruments are important for evaluating the subsurface structure of the moon, down to 1 kilometer or more depth, depending on the method. A variety of different tools are available. One is ground-penetrating radar. Ground-penetrating radar sends radio energy into the subsurface and looks at reflections, and from that can develop models of the crust underneath the surface. Lunar penetrating radar has been deployed on the moon, most recently by Chinese rovers that have obtained very detailed maps of the subsurface going down several hundred meters. Seismic data will be very important for lunar exploration. Seismic instruments were part of Apollo, and they will be important parts of future lunar exploration. Gravimetry is another key data set that was obtained during Apollo and will undoubtedly be obtained by future exploration. Gravimeters measure very slight variations in the gravitational acceleration on the surface and can be used to increase the resolution of data obtained by orbital assets. A number of geophysical instrumentation packages have been deployed on both the moon by Apollo, but also robotically on the surface of Mars. The InSight lander has been in operation on Mars and has successfully deployed geophysical instrumentation, including seismic and heat flow, and also environmental monitoring, including temperature, wind, and other sensors. This demonstrates that robotic assets can successfully deploy geophysical instruments as well as humans. And these are lessons that we can bring to the moon and then ultimately to other planetary surfaces and how to operate. Apollo deployed a number of geophysical instrument packages as part of the Apollo Lunar Surface Experiment Package, or ALSEP. It included a laser ranging experiment, which is still in operation, magnetometry, seismic, including both passive and active seismic, gravimetry, heat flow. All these sort of data sets are going to be part of future lunar exploration as well. A key data set for doing field geology is imagery and also close-range remote sensing. A lot of these technologies were not available during Apollo, and they can revolutionize what can be done with field geology. These include things like crew-carried cameras, very similar to the kind of suit-mounted cameras that were on Apollo, except now digital versus analog, rover-mounted cameras of various types, and also new technologies like LiDAR or even low-altitude aerial imagery. Imagery can be collected in visible as well as other wavelengths of light. On Apollo, there was a television camera mounted on the Lunar Roving Vehicle, or LRV. This was controlled remotely from the ground, and it was used to collect context imagery for the crew activities on the lunar surface. Recently, in analog tests here on Earth, like Desert Rats, similar sort of camera for a similar purpose was mounted on the top of the rover. This camera was a gigapan camera that collected still imagery that could be stitched to produce very high-resolution panoramas for the purpose of monitoring EVA activities, as well as for capturing context of field sites. For crew-mounted cameras, the Apollo astronauts had at their disposal a number of high-quality film cameras, including 70mm Hasselblad cameras and a 16mm movie camera. They used these in the field to obtain images of samples and also to obtain panoramic imagery for site context. There were a number of drawbacks to the Apollo cameras. One was because they were analog and required film, there was a limited number of film frames that they could take because of mass volume constraints that limited the number of film cartridges they could take to the lunar surface. In addition, the still cameras required a fair amount of training in order to get the astronauts acclimatized to the correct procedure for taking panoramas. And also there was no real-time imagery that was available, unlike the digital imagery that we can obtain with modern cameras. Modern cameras, which are essentially miniaturized, high-definition video cameras that can also take still frames, can fill a lot of the same roles that the Apollo cameras did, with minimal mass and volume, no consumables other than power, and also offering real-time data availability. There's the opportunity for minimizing the training compared to Apollo. No longer do the astronauts need to stand in one place and very carefully aim their bodies to take panoramas. Instead, by shooting video, they get a constant video feed of what's happening, from which high-quality still frames can be extracted. There's also the opportunity, since this is digital data, to enable advanced image processing techniques to produce data products that weren't previously possible. This includes three-dimensional models, 3D models, obtained with photogrammetric methods. What you can see in this image is an experiment that I did, taking about a minute of video taken with a GoPro camera from an EVA done from the International Space Station. The GoPro camera was mounted on the astronaut's spacesuit, taking video as the astronaut did the EVA, and in the software I was able to take these images and make a three-dimensional model of the station structure. The same technique has been applied to Mars imagery, and the benefit of this is you get 3D models of the terrain that's being explored, as well as camera position data that can be used as navigation data for operational awareness of the EVA. Another new technology is LiDAR, light detection and ranging. This technology uses a laser to shoot very rapid pulses of laser energy at a target. The reflection is used to build 3D models. And so with this technology, very precise three-dimensional shape models as well as reflectivity data can be obtained for outcrops on the surface of the moon. Another technology that's very commonly used on Earth are uncrewed aerial systems, or UAS, drones. These are used to obtain overhead imagery, deployment of various sensors, and on the moon, something like a UAS could be used to get standoff monitoring of EVA operations, as well as context imagery and three-dimensional models of the lunar surface. Other imaging technologies that can be used on the moon that are growing increasingly important in doing fieldwork here on Earth are close-range remote sensing techniques. This includes visible and near-infrared and shortwave infrared reflectance spectroscopy, forward-looking thermal infrared imaging, as well as laser-induced breakdown spectroscopy. Each one of these techniques can remotely obtain thermophysical, geochemical, and mineralogical information. Forward-looking infrared, for instance, can be used to look at the heat signature for caves. This is going to be important for places like the moon because subsurface cavities like lava tubes are a very important and attractive exploration target. Hyperspectral imagery using visible and shortwave infrared wavelengths is used here on Earth with tripod-mounted cameras to map out compositional variations in places like lava flows. With LIBS, scientists can obtain remote compositional information using a laser beam. This laser ablates a very small volume of rock, and the resulting plasma is analyzed with a spectrometer to obtain the elemental composition. This has been effectively deployed on Mars as part of the ChemCam instrument and can be easily deployed on a rover-mounted or even a handheld instrument on the lunar surface for future exploration. LIBS is one example of a in situ analytical tool that can be deployed with a hand-mounted instrument that an astronaut can use on EVA. There's a variety of other instruments that can also be used in handheld mode. This includes the visible near-infrared and shortwave infrared spectroscopy that I mentioned earlier. This also includes a technology called X-ray fluorescence spectroscopy, or XRF. XRF basically can give you semi-quantitative chemistry in about a minute without doing any sample preparation. The instrument's simply held up against the outcrop and can be used to distinguish samples and outcrops that may otherwise look similar. It can also be used to interrogate very fine-scale structures that couldn't otherwise be sampled. Another X-ray technology is portable X-ray diffraction. So this instrumentation in its miniaturized form can be taken to the field or used in a surface habitat and can be used to obtain crystallographic information that, along with XRF, can be used to identify mineral species and obtain other compositional data. So X-ray fluorescence and X-ray diffraction, XRF and XRD, are two examples of the sort of miniaturized laboratory methods that can be deployed on the lunar surface or in a lunar habitat. These instruments, as well as others, have also been used on the surface of Mars. So the Mars Surface Laboratory rover has on board an XRF and XRD. It also has the LIBS in the form of ChemCam. It also has on board miniaturized mass spectrometry and other analytical tools that are used to do field geology. These sorts of tools can be used on the surface of the moon. They could also be used in a habitat. So rather than use the tool during an EVA, the astronauts can use the same handheld tool in a glove box in their habitat. This was tested during the Desert Rats field tests in a facility called the GeoLab. The GeoLab allowed the astronauts to use XRF in a closed environment that had airlock access to the outside, where samples could be brought in for examination using XRF as well as microscopy. And this is a template for the kind of habitat analysis that could be done for future lunar exploration. Another field task that is critical for lunar exploration is sample collection. EVA astronauts on the lunar surface must be able to recognize, access, document, and collect relevant and scientifically useful samples from key localities, and they must use appropriate and standardized methods for collecting and documenting those samples while maintaining the sample's integrity. And this curation task is critical for increasing and maintaining the scientific utility of those samples moving forward. One challenge that the Apollo astronauts had during their sample collection tasks was the limited mobility afforded to them by their EVA suits. The A7L and A7LB suits worn by the Apollo astronauts limited their ability to bend over, limited their shoulder motion, and as with current EVA suits, they had limited dexterity with their gloved hand. So all these limitations limited the kinds of activities that they could perform, and to accommodate this, special tools and procedures were designed to allow the EVA crews on Apollo to collect samples. Now, the tools that they actually use are really adaptations of standard tools that are used here on Earth that would be familiar to any field geologist. But the tools themselves changed somewhat from mission to mission as experience was gained about what worked best. Now, the new generation of tools for the next generation of lunar surface exploration are going to use those tools as a starting point, but the new EVA suits and new procedures may make some of the Apollo approaches unnecessary or may require new ones. An important thing to understand, though, is that continued test and development of even simple tools is required. But also remember that some of these tools need not be reinvented from the ground up or made overly complex. A good example is a rock hammer. A rock hammer is a rock hammer, both here on Earth and on the moon. You can see here in this image a couple of Apollo crew members during one of their training runs on Earth, and how they're having to awkwardly bend over in the bulky spacesuits they're wearing. One of the main drawbacks of sampling in the Apollo suits was the fact that it was very difficult to do this as one person. So for a two-person EVA, collecting a sample often required both of the astronauts to be engaged in that. Future exploration will need to streamline this so that the two astronauts or more astronauts on the lunar surface could more independently work and therefore increase the efficiency and use of time on EVA. So on Apollo, the astronauts followed a procedure for collecting samples that used a variety of tools at their disposal. They had tongs to pick up rock samples since they couldn't bend over. They had scoops and trenching tools, again, to dig into the lunar soil. The astronauts had rakes that they used to collect pebbles from the regolith. All these tools had long handles, again, to accommodate the fact that they couldn't bend over very readily. Hammers were used to break rock chips off, but also used to drive instruments and core tubes into the lunar soil. Versions of these same tools will be used for upcoming next-generation lunar surface exploration. For sample documentation, the astronauts used their cameras, as well as a device called a gnomon for scale and also for color reference to document their samples with imagery. Photos were taken for various angles and also under different lighting conditions, and the gnomon was used to also determine local vertical as well as the orientation of samples. A lot of this can be done digitally with next-generation exploration using cameras and photogrammetric methods to obtain 3D models of the sample site both before and after. Sample collection protocols similar to Apollo have been tested on recent analog missions like Desert Rats. This chart here shows the field geology protocols used during the Desert Rats 2010 field test. The important thing here to recognize is that even experienced field geologists need checklists. And that's especially important for planetary field geology, where the sample curation process and making sure that all context data is collected for samples is critically important. So a critical part of the sample collection process is then returning samples to Earth in a curated fashion. So for Apollo, samples were placed in individual bags that were individually numbered. A small number of the samples were placed in special environmental sample containers that were meant to keep the samples from being contaminated by atmospheric gases here on Earth. Ultimately, a small number of the lunar samples have been studied in detail, something like 16% of the 382 kilograms of material that was returned. For future lunar exploration, similar amounts of material returned to Earth should be anticipated. Sample curation is critical for samples that are collected on the lunar surface. What curation refers to is the proper field identification, collection, documentation, packaging, transport, contamination protection, and preservation of the samples. And curation will set critical engineering requirements for future lunar exploration. This includes the design of spacecraft, surface systems, facilities on Earth, and even training of crew and the mission science team. The field analysis tools I mentioned earlier, like the in situ analysis using XRF and other tools, are going to be critically important in the curation process because they're going to enable sample selection in ways that weren't possible during Apollo, and also high grading of samples, that is down selecting samples that would be returned to Earth versus those that would be kept on the moon without return to Earth. That's going to be very important for very strategically planning the amount of down mass and down volume that's going to be returned from future lunar exploration. An important consideration for sample collection and curation is that designs for surface systems and spacecraft provide sufficient sample return mass and volume for terrestrial studies. The Apollo missions returned as much as 110 kilograms of sample. That was on Apollo 17, independent of the packaging. This down mass is important to retain because terrestrial scientists are going to require sufficient amount of material in order to do the kinds of geologic and geochemical investigations that need to be done to answer science questions. Another important consideration is contamination. Contamination of samples can come from a variety of sources at any stage in the sample collection process. This even includes pre-mission design and manufacture of tools. So it's going to be important to make sure that tools are designed and made of materials, for instance, that do not contaminate samples. A good example of this is on Apollo. There was lead contamination of some of the core samples because of what the core tube tools were made of. They contained a lot of lead. Another important consideration for future lunar exploration that's going to collect samples that wasn't necessary for Apollo is the refrigeration of some samples. Environmentally sensitive material like volatiles, which are a very important science and exploration target for exploration of the lunar poles, that material is going to need to be environmentally stabilized and kept at low temperatures. Freezing technology developed for the ISS has demonstrated that samples can be kept at temperatures of as low as minus 80 degrees with the mass and power budget of a spacecraft. And future hardware development may be able to exceed that. And those sorts of capabilities are going to be important, as well as others defined by the lunar science community for future lunar exploration. A lot of data is going to be generated during lunar surface operations. Some of this data is going to be in the form of imagery. Or for a field geologist here on Earth, a field geologist will often make sketches, take photographs, and all these are critical visual parts of a geologic data set. They allow the geologist to quickly highlight important features and document context in a visual manner. And not having that is a critical loss to science return, because understanding can be lost, context can be lost. That ultimately leads to uncertainty about the context of the field site that was visited and an inability to test geologic hypotheses. For future lunar exploration, a lunar astronaut's not going to be able to make sketches in a field book with their gloved hand. Instead, photo documentation is going to be very critical. It's going to be critical for astronauts to be able to obtain large-scale and also small-scale panoramas from a variety of vantage points, both at the outcrop scale but also at the sample scale. It's going to be important to obtain both before and after imagery of sample locations with a device like the gnomon to establish scale. It's going to be important to get photo sets or video imagery with the appropriate geometry so that photogrammetry can be applied to generate things like 3D models. And all imagery, especially since it will be digital imagery, should be time-coded to a common time format and also geolocated so that this data can then be integrated with other data sets. One notable absent imaging technique that was not available in an easy way to the Apollo astronauts is microscopic imagery. A field geologist here on Earth is typically equipped with a hand lens in the field. And it's difficult to use a hand lens when you have a visor covering your face. Modern digital imagery technology could replicate the use of a hand lens to obtain microscopic imagery to reveal and document textural relationships at a small scale in a rock sample. For recent analog field tests like desert rats, a variety of these kinds of imaging technologies were used. So on the desert rats field tests, the test subjects wore backpacks that had video cameras that were tied to the voice communication system that the crew members had to obtain field notes. And these voice/video field notes included both imagery as well as verbal descriptions. These verbal descriptions fill the role that a traditional geologist field book has. A field geologist is constantly writing down descriptions in their field book along with their sketches. These provide context that can be used to assess the relevance of ongoing work as the work progresses. It can be used later on to review the day's activities, to annotate and collect field descriptions. All this information can be reviewed later on so that the geologists can be updating their field plans and their multiple working hypotheses. For the next generation of planetary exploration, all this should be done digitally, and since geologists in a spacesuit can't write in a field book, done verbally. This data should be time tagged and searchable by both the crew and also the mission support teams. The end result would be something like an annotated transcript of an EVA, something very similar to the Apollo Lunar Surface Journal, although made in real time. And this data should be accessible in real time to all members of both mission support as well as the crew. Another type of data that's going to be collected on the surface of the moon that's similar to data collected by terrestrial field geologists is spatial data. Now, without a global positioning system for the moon, this is going to be difficult, but it's going to be key since geology, being a spatial science, is dependent on the spatial context of data that's collected. This data is going to be in the form of imagery, sample locations, the locations of instrument and tool deployments, point data that's obtained by these various instruments. This should all be organized not just in sort of a time sequence, but also in a geographic sense. On Earth, this is done in the field with modern mapping technologies with GIS software, Geographic Information System software. So at UTEP, we map with tablets in the field with our undergraduate students, and these tablet computers running GIS software show the real-time position of the user using GPS. Something similar to this capability would be very useful on the surface of the moon for EVA, but also for mission control and the mission science team back on Earth. All the data in this GIS should be registered against a common map base, something like pre-mission satellite data, with a sufficient resolution so that details can be seen for navigation and also traverse planning purposes. The users of this spatial data should be able to view the map base at a sufficient resolution to indicate precisely where they are in real time. So this could be the crew out on EVA. This could also be mission support back on Earth. The users of this spatial data should also be able to view the collected data in near real time within the context of their immediate surroundings. And that is to ensure that there is scientific situational awareness, so that the crew members and also mission support have the data that they need in order to test and refine their continually evolving multiple working hypotheses. In order to do all this, one technological requirement for future lunar exploration is the establishment of some sort of lunar geolocation infrastructure, whether that's in the form of beacons on the surface or, going back to previous ideas for lunar navigation, the establishment of a network of communications and navigation relay satellites. Whatever the architecture, the navigation capability on the lunar surface will be critical for data collection. Now, ultimately, all this data, image, map, spatial data, needs to be displayed to the crew in some way. And this is both the crew inside habitats and vehicles, but also out on EVA. These display devices will need to provide navigation information and also situational awareness data that can be viewed at various scales. It should also allow the crew members to view collected imagery and geologic data in real time, again, within the context of their immediate surroundings. And these display devices, especially for EVA crew, should probably also display things like checklists of procedures, as well as give them situational awareness for their equipment. Mission support can also use these same sort of display technologies in collaboration with the crew for debriefs and planning sessions. This can be in the form of virtual reality environments, something similar to a Microsoft HoloLens that's used by JPL now in the exploration of Mars data. For EVA crews, this interface and display technology might be in the form of a heads-up display, something that can be used basically without the requirement of manual dexterity in a gloved hand. So something that can be controlled with voice commands, that has the capability for voice recognition and voice transcription. This image shows a prototype of a heads-up display goggle device that was tested at Desert Rats in 2011. More recently, some of the NEMO activities have tested underwater U.S. Navy diver augmented vision device technologies, basically a heads-up display that can be used by a diver in a helmet. These sorts of display technologies that can show in the user's field of view data are going to be important technologies for surface exploration of the moon. To manage all this data, it needs to be managed in a ground data system of some sort. This ground data system basically needs to organize the data both spatially and temporally. Spatially, that would be in the form of the GIS. Temporally, it'd be in the form of some sort of a timeline organization of the data. The data management system will allow researchers here on Earth, as well as the crew, to establish the field setting of each return sample, as well as all the downlink data that's collected during planetary exploration. This data management system should include tools to plan and monitor ongoing operations while they're happening, enable three-dimensional visualization of data as it's being collected, provide searchable documentation of the data after it's collected, and also be simultaneously accessible by both the surface crews and mission control and mission support back on Earth. So to do all this, it's going to require hardware, software, communications infrastructure, and geolocation infrastructure. There's been some prototypes to these sorts of ground data systems that's been developed for Earth analog activities. One of them is the XGDS system developed by NASA Ames that's been employed in a wide variety of analog tests here on Earth, including NEMO. Another good analog to this sort of technology is the timeline-based display of Apollo data that is excellently shown by Apollo17.org. So if you go to that website, you can see the Apollo 17 mission organized in terms of time, with photographs, video, transcripts, all organized in a timeline. Very similar to what might be done in future planetary exploration. Ultimately, all the data will have to be curated, just as the samples are curated. The ground data system would be the first step in doing that. For Apollo, the curation of the human activities on the moon is being done in the context of the Apollo Lunar Surface Journal, as well as various parts of the NASA Planetary Data System, or PDS. Surface science operations on the moon are going to require mobility. They're going to require access to terrain far enough away from the landing site in order to avoid sample contamination from landing plumes, and also to avoid disruption of surface assets from ascent plumes. Mobility is also going to be required in order to gain access to study sites at various distances from where the landing occurs. Walking EVAs may or may not be sufficient in order to do this. At least several kilometers of distance may be required to access targets of interest, depending on where those targets are with respect to the landing. Roving capability is useful, as it was with Apollo, because it lowers the metabolic cost of doing EVAs. And this can extend the EVA time and allow access to more distant targets within a given amount of time. And Apollo is a great example of this. During Apollo, they had the lunar roving vehicle for Apollos 15, 16, and 17, the J missions. Now, that afforded them kilometers of range away from the landing site, as compared to Apollo 11, where the EVAs were confined to just a few hundred meters around the landing site. So this figure shows the disturbed area around the Apollo landing sites, and you can see that the distance of the disturbed material extends for up to a few hundred meters away from where the landing was. And the non-circular shape is due to the topography and the trajectory of the ascent vehicle. To help with mobility on some of the Apollo missions, like Apollo 14, the astronauts employed a modular equipment transporter, essentially a little rickshaw cart that they could use to transport tools, equipment, and samples. Ultimately, that was not a very successful operation, and so the Apollo J missions used a lunar roving vehicle, which afforded them great mobility over kilometers away from the landing site. So similar mobility will be needed for future lunar exploration. Analog tests here on Earth have tested a variety of different mobility solutions, including things like the Chariot rover, the multi-mission space exploration vehicle, also known as the Lunar Electric Rover, small pressurized rover. During Apollo, there were even ideas of using small electric motorbikes on the surface of the moon, and one can imagine a variety of other solutions for mobility, including things like off-road segways or even robotic type assets. Robotics are going to be critical for future lunar exploration, not just in terms of mobility, but also in terms of the most effective use of surface time. So robotics are going to be important for essentially offloading from human explorers those tedious and time-consuming tasks that are involved with things like deployment and operation of geophysical and other instrumentation, or the use of in situ analytical instruments that have long dwell times, or for exploring places and targets that might be inaccessible for various reasons for humans to access, places that might be too dangerous, or where the topography makes access impossible. Intelligent robotic assets could fill a variety of roles. They can conduct reconnaissance before a mission. They can do active exploration in parallel with the humans, essentially acting as robotic field assistants. They can passively monitor human exploration activities, essentially being a third-person sort of documentarian of activities as they're ongoing. Robotic assistants could carry materials and equipment and aid in mobility. And then ultimately, robotic assets deployed during human exploration could conduct robotic follow-up to the activities conducted by the astronauts. Training of crews will be critical for next-generation lunar surface operations. Since 2008, NASA has selected 3 classes of astronauts, and the science training they have received, in particular the geology training, has been unlike that received by space shuttle-era astronauts. The focus now is on expeditionary missions to the ISS and ultimately beyond, and similarly, the geology training has been focused on the toolkit that these individuals will need in order to make the observations and decide on the importance of those observations and how to effectively communicate them when they get the chance to go to ISS or another planetary surface. The training now has 3 phases, and each phase provides the crew members with the background they need in order to do lunar surface mission tasks ultimately. The Phase 1 training is the basic geologic training that's conducted as part of the astronaut candidate training flow during the first 2 years that newly selected astronauts are with NASA. It involves 2.5 weeks of classroom instruction as well as 2.5 weeks in the field. The classroom instruction focuses on major geologic principles and also on forensic thinking. How and why geologists generate multiple working hypotheses, and how observation, documentation, and decision-making is done in testing those hypotheses. The classroom instruction has a lot of hands-on activities as well as speakers from both NASA and also academia. The Phase 2 training, also part of the basic ASCAN training, is 2.5 weeks in the field in sites in northern Arizona as well as northern New Mexico. And during this training in the field, the new astronauts practice and implement the geologic principles they learned in the classroom, with a focus on linking orbital observations to the surface, this notion of outcrop to orbit. It includes planning and flexible execution of traverse plans to address science questions in the field, making and documenting critical observations, developing and testing hypotheses as a field geologist would, and experience with using some of the in situ analytical tools like X-ray fluorescence spectroscopy and other tools that they might use eventually on the lunar surface. And another important part of the geology training is expeditionary and team building skills. So we've taken them to a variety of places like the Grand Canyon, Meteor Crater, and sites in the San Francisco volcanic field in northern Arizona, and the Rio Grande Gorge in New Mexico. The Phase 2 of the geology training is intermediate training the astronauts get in the time between they complete their astronaut candidate or ASCAN training and assignment to a mission, whether a mission to ISS or in the near future, a mission to a planetary surface. This training includes field assistantships that the astronauts can have the opportunity to take part in. During these opportunities, the astronauts are partnered with professional research geologists on projects, and the astronauts participate in activities like sample collection, mapping in the field, instrument deployment, and data analysis. And this is a mutually beneficial activity. The astronaut gains more field experience, this time in a research setting rather than a teaching setting. And then the principal investigator who hosts the astronaut gains the outside-the-box perspective that astronauts tend to have. Another part of the Phase 2 training is what is called engineer-manager training. These are opportunities for senior astronauts to experience some of the field component of the Phase 1 training along with other NASA personnel. These other NASA personnel are engineers and management and leadership positions at NASA, and it gives them the opportunity to understand the field operations that astronauts would be engaged in on planetary surfaces. Another component of the Phase 2 training is participation in hardware operation and science deployments. This includes analog field tests, things like NEMO, Desert Rats, both of which are NASA analog programs, and also other programs associated with the European Space Agency, like their CAVES and Pangea programs. Each one of these activities involves integrated field tests where science is done in the context of operations and hardware testing. And the astronauts bring their operational expertise to conduct these tests in concert with scientists and engineers in order to achieve specific goals. Phase 3 training ultimately will be the advanced mission-specific training that crew members will get prior to their flight. And this is going to be patterned after the training that the Apollo astronauts, in particular the Apollo 15 to 17 astronauts, received prior to their missions. On average, they had one geologic training trip a month leading up to their missions. And the reason why this is important is because geology training is cumulative. It's based on experience, and it's also perishable. If you don't do geology for a while, you kind of get rusty. The central goal of the geology training for Apollo, as it will be for future planetary exploration, is to develop crew members that can, with some guidance, operate without constant guidance. There's a need for independence, and that's going to be largely driven by limited time on the lunar surface. The Apollo astronauts successfully did this. They had the training necessary, and they demonstrated that on the lunar surface, and it allowed them to operate as independent agents that were able to make decisions based on the geology they were seeing on the ground. And the high quality of the samples and the data that they collected reflects the depth and the breadth of their training and the enthusiasm that they ultimately develop for field geology. And that's something that we are trying to successfully replicate now with the post-2008 training that NASA astronauts receive. An ethos that we're trying to bring from the Apollo training is this notion of the 3 T's, as Jim Head says. That's train 'em, trust 'em, and turn 'em loose. Each Apollo 15 astronaut, for example, experienced over 1,000 hours of geology training. About 375 hours of that was general geology training, and 660 or more hours of that was mission-specific training. And a large part of that, 470 hours, was in the field. The Apollo astronauts were in the field a lot. Between May 1970 and November 1972, there are 375 different field trainings at 27 field sites. There are 59 experienced field geologists engaged in this training of the Apollo 15 and 17 crews. And this training included not just the instructors and the crew, but also mission scientists, flight controllers, flight directors, and other mission personnel. And they went to a variety of places in the desert southwest of the United States, Hawaii, Iceland, and other sites that are good planetary analogs for the kinds of geology and terrain and scientific questions that they were anticipating. The same thing will need to be done for future planetary exploration. We need to instill in the crews that will ultimately go to the moon again these 3 T's of train 'em, trust 'em, and turn 'em loose. And the enthusiasm for the science that the Apollo astronauts got from their experiences in the field, learning geology. So the training must continue to include all the people that are going to be involved in missions, from instructors to crew to mission support. We need to train them as a cadre of team members. We need to train the operational mindset, because without the integration of operations and training, a mission has a lower likelihood of success. So another ethos that we want to instill is this notion of training like you fly and then flying like you train. In addition, future operations practices on the lunar surface are going to need to blend the human crew members' ability to integrate diverse data to reach unexpected conclusions, along with the ability of robotic assets to conduct tedious, time-consuming procedures. These 2 operations have not been previously integrated into a single exploration mission. Concepts exist for that integration and are being tested at various analog sites here on Earth, but more needs to be done to understand fully the best way to pair robotic and human exploration strategies. There's a variety of approaches that can be used for exploration of the moon. These involve all of the various tasks that I discussed earlier, from field observation to making field measurements, some with tools, some with imaging instruments, the deployment of surface instrumentation, including geophysics and environmental monitoring, the collection of samples. Some of these are going to require humans, some of them can be enabled by robots, and all of these will probably be able to be done optimally with a combination of the 2. In the end, it's going to be the scientific objectives, the specifics of the study site, and other exploration considerations that are going to place the constraints on which of these tasks is going to be the most important, and the surface architecture that's going to be required to realize it. As a thought